unpacking the characteristics of similar shapes from their geometrical transformation. Important. In working with the similar figures, you are expected to solve problems of relationships between linear, square, and cubic measures. This is a reference to size, areas, and volumes, and describe how changes in one of the measures of the figure affect the others. That is important. We note that the words shapes, figures, and polygons shall be used interchangeably to mean the same thing. So let us look at the relationship between ratio and proportion. Ratios are fractions and are a way of comparing two numbers, quantities, or variables by division. Ratios are written in three ways: 4:9, 4:9, 4/9. Those are the three ways we can write a ratio or fraction. A proportion is a statement that two ratios are equal. Proportions are written in two ways. Four values are used. This is the first way, and this is the second way. The four values here are, we have 3, 4, 12, and 16. These are 4, and the same can be said here again. Both are read as 3:4 as. That means the 4 dots represent the word as 12:16. So the relationship will then be a proportion is two equivalent ratios of fractions, right? So here is an example number A, 3/4 is equals to 12/16. That's a proportion, right? Then example number B, A/B is equal to C/D. But we note that B and D cannot take the value 0 because they occupy the denominator. Once that happens, then we have an undefined situation. Now, let us look at the relationship between ratio and scale factor. What is the ratio of the side EF to side BC? Side BC is marked 16, side EF is marked 12 of these given triangles, the pre-image and image. So to get their ratio is EF/BC, then we substitute with their values, and it reduces to 3/4. So that's the ratio between those two sides. What is the scale factor of the two triangles? Now we wanted the scale factor of the two triangles, but we should first note that a scale factor is a multiplier of the measure of each side of a pre-image to get the measure of each side of the image. So scale factor is equals to image over pre-image, and the reverse is not true. So a scale factor exists if the corresponding sides are in the same ratio. Same ratio is important. That is to say, D/AC is equal to EF/BC is equal to DF/AB. Same ratio. So the answer to our problem then becomes ratios of corresponding sides. We take the first pair, we find the ratio is 3/4, the second pair 3/4, the third pair 3/4. So we are getting the same ratio for the three pairs of corresponding sides. Therefore, the scale factor is 3/4. What is geometrical transformation? A figure or shape is transformed when its position changes. And when that happens, it is congruence transformation. So we note that translation, reflection, and rotation produce congruent shapes, right? This is pre-image and the image. Triangle ABC have moved to triangle A prime, B prime, C prime. So that is congruence transformation. Therefore, if two or more shapes or polygons are congruent, then their characteristics are they have same shape, same size, corresponding angles are equal, same area, and same volume. For that reason, congruence transformation always produces similar or like shapes. Now check how the word similar is coming in. Congruence transformation always produces similar shapes, right? So pre-image and image are similar. Again, the transformation could be the size change. This is what we call non-congruence transformation, and dilation produces non-congruent shapes. So dilation is the non-congruence transformation. Therefore, if the transformation of figures, that is pre-image to image, is dilation, then the figures have the same shape. Their corresponding angles are equal. The figures have different size. That is, the corresponding sides are proportional. They have different areas. They have different volumes, right? That is important because here we are now referring to the dilation. Oh, this is dilation, which produces the issue that we have the same shape, corresponding angles are equal. They have different size. They have different area. They have different volume. That is as a result of dilation. Now, having said that, what it means now is if I have this shape that is pre-image, which is a cylinder, right? So that cylinder as it is, it means now if we are to transform it to result in image B, again, it is still a cylinder. That is why we talk of same shape. Fig A is a cylinder, fig B is a cylinder. So they have the same shape, right? Corresponding angles are equal. Of course, we can only talk of that when it comes to the triangle, to say angle in B should be equal to angle in B prime, angle in C should be equal to angle in C prime, angle in A should be equal to angle in A prime, right? When you look at the different sides, you can see that the cylinder in A and cylinder in B, they are not the same, but they are both cylinders, but they don't have the same size. Again, the pre-image triangle ABC is not the same as triangle A prime, B prime, C prime, right? But they are both triangles, right? Then different area. If you find the surface area of the cylinder in A, it won't be the same as the surface area of cylinder in B. The same can be said, you find the area of triangle ABC, it's not the same as triangle A prime, B prime, C prime, right? Then we talk of different volume, right? Of these cylinders, if you are to fill this cylinder in A with water, the water that is going to get inside is different from the water that you are going to put in the cylinder in B, right? That is dilation for you. We are having different volume, different area, different size, but same shape, corresponding angles are equal. But why? This is so because dilation is as a result of multiplying by the scale factor the size of the pre-image to get the size of the image, while leaving the angle measures and the shape the same. That is an important fact that you should always remember, that dilation, the fact that we multiply with the scale factor, right? It is only going to affect the sides. Hence, when the sides are affected, we are talking of the change in what? In size. So when the size changes, then again, you can't expect to have the same area. You can't expect to have the same volume, right? But the angles and the shape are not going to change, right? Okay, for that reason, the pre-image and the image are similar shapes. That is, the diagram in A and B are similar shapes. The triangle ABC and A prime, B prime, C prime are similar shapes. Again, check the word similar is coming in, right? So we can now safely conclude that translations, reflections, rotations, and dilations always produce similar or like shapes. This is why I was saying we are going to unpack the characteristics of similar figures or shapes from the geometrical transformation. Therefore, when we have arrived at this, then we can safely now come up with the characteristics of similar figures. That is, if two or more shapes are similar, then their characteristics are they have the same shape, but not necessarily the same size. This is so because congruent transformation, obviously, the size will be the same, but non-congruent transformation, the size will be different. So we are simply saying when we say they have the same shape, that means the cylinder will remain a cylinder. Whether the other one is bigger or smaller, but the cylinder will be a cylinder, right? Their corresponding angles are equal. They have the same ratio of the corresponding side. This same ratio is what we refer to as the scale factor. Corresponding diagonals are in the same ratio as the ratio of the sides. The ratio of the areas is the square of the ratio of the sides. The ratio of the volume is the cube of the ratio of the sides. Let us look at this example. The relationship between linear, that is side ratio, square area ratio, and cubic volume ratio measures allow us to describe how changes in one of the measures of the figure affect the others, right? So here is a situation. I have these rectangular cubes, right? And I've indicated one side of the smaller one, which is A, and the other side of the bigger one, which is B. So I'm simply saying now, if the length ratio is B over A, to get the area ratio, you simply square the length ratio. To get the volume ratio, you simply cube the length ratio. This is the relationship between the side ratio, area ratio, and volume ratio. So that if you are given the volume ratio, you can actually calculate the length ratio by finding the cube root of the volume ratio. The same can be said if you are given area ratio, you can actually find the length ratio, you can actually find the volume ratio. So it's very important. This is what is tested, that do you know the effect then if we change the length ratio, what will happen to the area? What will happen to the volume? Okay, let us look at key takeaways from this presentation. The concept of similar figures and congruent figures are two different terms that are closely related. All congruent figures are similar, but not all similar figures are congruent. That is very important to note. The two conditions for similarity between shapes are: one, corresponding sides are in the same ratio, and that is the scale factor, and corresponding angles are equal. Now, you need to know that these two conditions for similarity are necessary for polygons with more than 3 sides, because, for example, these are two polygons, rectangle 1, rectangle 2. They have more than 3 sides. So all what we want to check is, are they similar? By checking whether they satisfy condition number 1 and condition number 2, both of them. So to start with, if I am to find the ratio that is side DC, which correspond to side EF, right? Then thereafter, I have to find the side ratio of EG, which corresponded to A, D, or DA. Then if they give me one and the same thing, then I can safely conclude that the two given figures are similar. So this is the ratio DC over EF, which is 3/4. Then DA over EG, which is 1/2. Already, these two are not the same. They are not giving me the same ratio. They are different. This is where in the way the same ratio comes in. And same ratio will be referring to the scale factor. So the fact that they are different, then we say the rectangles are not similar because their corresponding sides are not in the same ratio. We don't have a scale factor. But of interest, if we were to check condition number 2, whether the corresponding angles are equal, you realize that all the angles are of 90 degrees of the respective figures. So condition number 2 is satisfied, but condition number 1 is not. So this is why it's always necessary for polygons with more than 3 sides, you need to test all the 2, right? Let us go to another important thing. To determine similarity of triangles, it is sufficient to show that the corresponding angles are equal only. That is condition number 2. You don't worry about condition number 1, whether the sides are in the same ratio. This is so because multiplying by the scale factor the measures of side of a pre-image to get the measures of the side of the image leaves the angle measures and the shape unchanged. Right? I think I talked about this when I was referring to the scale factor. Its effect, it doesn't affect the angles, doesn't affect the shape itself. If it is a triangle that is being transformed, the result is a triangle, whether bigger or smaller, but still a triangle. So for us, when we show that the corresponding angles of triangles are equal, we can safely conclude that the sides are in the same ratio. hence triangles similar. This is a very important observation, and always remember that if we are to check whether two given triangles are similar, it's enough just to check at their corresponding angles. When the corresponding angles are equal, then we can conclude that the corresponding sides are in the same ratio, for the reason that the effect of multiplying by a scale factor don't affect the angles nor the shape. Okay, with this, I would want to say kudos to you for watching. Please like, comment, share, and subscribe.